Okay, hi everyone. We might get started since we've got a lot to cover and other people can join or catch up on the video later on. Okay, today we're going to try and cover peering. Peering is a process by which all the OSDs reach agreement about the state of all the objects and the metadata of those objects that reside in the PGs that they're responsible for. The process is driven primarily by the primary OSD, almost exclusively by the primary OSD, and it's implemented as a boost state chart. As a boost state chart state machine. So it's a state machine implemented using the boost state chart library. And that state machine is embedded in each PG. So for every PG, there will be a state machine. So just before we go any further, I'll just mention a few docs that are worth looking at. The first one is the one that's currently on the screen that I hope you can all see. And that's talking about last epoch started. The next one I'd recommend as reading is Sage's thesis, and specifically section 6.3, where he covers a lot of the concepts involved. Then there's the Boost State Chart Library. Because the peering process and some of the associated processes, such as recovery, etc., are implemented as a state machine, it's a great idea to be able to understand how the state machine works, to be able to navigate your way through the code. This tutorial is quite good at introducing you to the concepts of the state machine. The way the state chart state machines work is you have a series of transitions. You have a series of states, and then the transitions are implemented either as a transition, which can be called explicitly, or by issuing events within the state machine, which are interpreted by various states and can be interpreted by multiple states. But we'll go into that more as we go through the code. The last document is the peering document. I'd recommend looking through that as well. I'll try and include these links in the description of the video somehow, or in a comment under the video. At the bottom of the peering document, you'll see this graph, which is a representation of the state machine and the flows within the state machine. It's not very useful when you look at it as part of this document, but you can download it and zoom, because it's an SVG, it zooms really nicely. But basically, if we look at it here, that's the entire state machine. So we're not interested in all of it. We're primarily interested in the role of the primary, and probably more specifically for today, this peering section. So I'll attempt to cover that, but we may transition into the activate session as well, because part of that's relevant. Okay, so when we enter the recovery machine, we go straight to an initial state, which is this state over here. So that's the default state of the recovery machine. So if we have a look at the recovery machine in the code, can everyone see this okay, or do I need to increase the font size? Or
it looks fine, but you could just increase it by one more size. That helps. Yeah, that's better.
Right.
Thanks.
Okay, cool. So here we see the definition of the recovery machine, which is a boost state chart state machine. The state chart, boost state chart, uses the curiously recurring template mechanism quite extensively. So quite often when you're implementing a derived structure or class, the first template argument is the actual derived class itself. So that's just a quirk of this particular implementation. So, but what we also see here is in the definition, we're passing initial as the second argument, template argument, and that is indicating that that's the initial state. This is in pg.h, and the implementation of peering is almost exclusively in pg.h and pg.cc. So we'll primarily or almost exclusively be looking at those files. Go down in this definition, there's actually a listing of all the possible states, up to date as far as I know. So we enter the recovery machine and we transition to the initial state, which is the default state for the machine. From that state, so we're sitting in that state, and the OSD will call, depending on whether this PG is being created or it's being loaded from disk, the OSD will call handle activate map or handle initialize. And in those functions, we will create a state machine event. In the case of handle activate map, we create an act map event. And in the case of handle initialize, we create an initialize event. And we tell the state machine to handle that event. So in other words, we post that event to the state machine. And if we go back to our graph, we can see that when we're in the initial state, if we get an advanced map, an act map, or an initialize, we then transition all the way over here to reset. And we can see that in the code by looking at the initial state. And we can see that we're reacting to the event. Bear with me a second. Okay, we can see here, this is a transition saying that when we get an initialize event, we transition to reset. Okay, so if we look at the reset state, useful. So the other instance where we can come to the reset state is if we'd already gone through peering and we're basically active and clean. When the map changes, the OSD will make sure that we get to see that map, and so that's worth looking at. We would get to see that in the started state, and that comes through as an advanced map event. So when we see that, we call should restart peering on ourselves, and if that returns true, we then transition to reset. So regardless of whether we're being created, whether we're being loaded off the disk, or whether we're already in an active and clean state, we end up transitioning to reset. There. We then receive an act map event, which is this line here. And if we look at how we react to that event, resets down. So act map, that's this definition here. So this is our reaction to the act map event. So we do some checks and then transition to started. So that, if we look at the graph again, we're now entering this state here, and we can see that, we can see the transition. We've gone from initial, following this line because of an act map or an initialize, reset, and then reset has a line here that when it receives an advanced map, that line, one of these lines here, actually goes from reset to that started box. Okay, and the boxes represent a context. Once again, it's a state machine concept where states can be grouped with under a concept, a context, I'm sorry. So whenever we're within one of these boxes, it means that that state is active. So when we're in primary or peering, we're still in started, we're still within started. So started can still be receiving events. So that's it's important to understand that, to understand how the state machine works. So we can be in a sub-state such as peering here, and started can still receive an event and do something, based on that event. All right, so continuing on, we've entered reset. and then transitioned through our return here. Our return from this function is saying we're transitioning to started. So I'd also recommend that looking at the logs, following the logs, with debugging set to 20, for example. That's usually the default debugging value. If you follow the output in the logs, as we enter each state, there's a notification set in the log, and also as we exit the state, each state will put an entry into the log to say that it's exiting. So you can follow the transitions between states from the log messages, and that can be handy in understanding how the transitions are working. So if we now look at the started definition, we then we need to look at so we go into the constructor of the start state, and then we make a decision based on whether we're the primary or not as to where we're going to transition. If we're primary, we transition to the primary state. If we are not primary, we transition to the stray state. And I think we probably, most of us know the stray state is a state we go into where we are holding relevant objects, and we may be required for either backfilling or logs, etc. So we stay in that stray state and either transition into to become one of the replicas or part of the acting set, or eventually, if it's decided we're no longer needed, the primary will tell us to delete, that we're no longer needed, and we can delete any objects that, or delete the PG, basically. So when we post that event, make primary, that forces the transition into the primary state. So if we look at primary, okay, we enter the primary state. And from there, I'm looking for the transition, but it's a default transition. So unfortunately, this involves a lot of flicking between the header and the implementation. So this is our primary state. Can see from this definition someone whoever's typing, can you mute, please? So in this definition, it's slightly different to what we've seen before. We now have 3 arguments, template arguments. The first is the derived class itself, as stated before. The second is the context, which is the parent state. So we're in primary, the parent state or the context state is started, which we've seen before, but then we have a default transition as well. So the default transition, when we enter primary, we go straight into peering. So if we look at that peering, we can see that when we enter peering, we go directly into the get info state. So we need to look at that. So once we enter get info, there is no default transition. So in order to see what happens in get info, we have to go back to the CC file. Oops, excuse me. Look at get info. So in this state, we look at the past intervals. So we work out our prior set. By building the prior set. So in check past interval bounds, we're looking at the map or the maps or the most relevant parts of the map to work out what our past interval bounds should be. So we know what intervals we have to cover. Then build our prior set. So once again, we're looking at the map, working out what set of OSDs we need to query. Okay. Then we call the actual function getInfos. So in getInfo, we're sending a query to the other OSDs to get the pginfo T structures from them. And if we look at pginfo T, is a summary of the PG statistics for the PG. It includes eversion Ts, which are a combination of the epoch and the version number, which is constantly incrementing, sorry, as changes come in. So So we keep a record of, in the PG info T, each PG on each OSD keeps a record of the last update, last complete, last epoch started, which is relevant to our discussion, or very relevant to the peering discussion. Last epoch started is the last time this PG went active. So once this PG decides all changes, it will declare itself active and it will update last epoch started. Also included in the PG info T structure is a PG history T called history. And if we look at that structure, we want one. Don't. Okay, so this is a PG history T structure. It also has a last epoch started. So the reason why there's two of these, we'll hopefully get into this more later, but the reason why there are two is when the PG declares itself active on the primary and goes into activate, it will set its last epoch started in the PG info T. But it's only when it knows, only when the primary knows that all replicas are activated and all have committed that last epoch started, that it will set last epoch started in its history, in the PG history T structure that's embedded in the PG info T. The reason it does that is when it calls activate and sets last epoch started there, it can then accept writes. And so as it will then instruct the replicas to write that down and to commit it. And that may be part of the first write that it sends to them. So once they've done that, they will then acknowledge that. And once where we receive the all replicas activated event, we then update history, and that becomes more relevant later on in the process. So we'll continue on. So recall get infos. We look at that definition. This is where we're asking for the info from each peer. So we've decided on a list of peers, relevant peers, and we are probing them for their PG info. So once we have all of those, the get info state will receive a got info event. So we look for that. pg.h. We can see that in getInfo, when we receive a GotInfo event, we transition to getLog. So once all OSDs have replied with their info, we then generate that GotInfo event and transition to getLog. So if we go back to .cc file, yeah, we can see it there. So we're posting the event GotInfo. So yeah, so sorry, we call getInfos. We ask for the infos, we get them back, we post an event. Once post peer info requested is empty, and we know that we've received all the peer info from all of the peers, we post the event GotInfo, and we transition to the getLog state. So let's have a look at that. So from here, we can we decide, we call choose acting, and we find out whether we can actually decide on an acting set. And this is the guts of the peering process, really. If that fails, we then need to decide whether we generate a need acting change event, in other words, change our acting set, or whether we go to incomplete, the incomplete state. So if we look at that visually, we're now in getLog. We can see that if we generate is incomplete, we go to the incomplete state. If we receive a GotLog event, we transition to get missing. But what's interesting is the choose acting event, choose acting function. So if we look at the definition of that, we're calculating the desired acting set, and if it differs from the current acting set, we'll request a change from the monitor. So in order to do that, we need to find the best info, and therefore the best log, or the most authoritative log that we can find. So we do that in this function, find best info. Okay, so when we're looking for the best info or the authoritative log, we're going to prefer a log that has a newer, an info that has a newer last update, or one that has second priority is a longer tail, and third priority is we're going to have a preference for the current primary. So you can see that, yeah. So we've built a list of the prior set in getInfo, and we've generated our list of infos. Just bear with me a second. Okay. So in Choose Acting, we combine the info from the peers with our own info, and then we feed all of that as an argument, the infos argument here, into find best info to calculate the authoritative log. First thing we look at is the maximum history.last epoch started available amongst all peers, including ourselves. So if you remember, history.last epoch started is relevant because that's the last time the PG as a whole went active. And was able to accept writes. So the PG as a whole was able to accept writes, so we can be confident peering completed successfully, and that epoch, in that epoch, and that all the OSDs in the acting set at that time will have recorded all writes act to the client prior to this epoch. We also know that all acting OSDs for that interval must have recorded all writes acknowledged to the client during the interval that begins with that epoch. Sorry if that sounds a bit jargony, but it's kind of a difficult concept to portray, and you've really got to think about it. We then check if any peer, including ourselves, has a last epoch started greater than or equal to the maximum history last epoch started that we've found. And we set a minimum last update based on that. So that's what all this is about. So if peering is going to fail, it quite often fails here, and this is where we'll go to the incomplete state. Yeah, so okay, so we set the minimum last update based on the last update field from the info that we've determined to be authoritative. Last update field is a pair of values, the epoch as mentioned before, and monotonically increasing version number. So we check last epoch started here instead of history.last epoch started, since any peer with history last epoch started set to a particular epoch must have at least that value in last epoch started, and may have a later value indicating it is completed activation at that epoch. But the PG as a whole did not go active since history.last epoch started shows a lesser epoch. So we depending on how that all pans out, we'll either return infos.end, which we're doing here, which will be interpreted as a failure, or we return best is the iterator to the PG underscore info T in infos that represents the best the most authoritative info PG underscore info T and therefore log that we could find, or it will equal infos.end, which once again is interpreted as a failure. So once we've done that, we then ask for that log, us the relevant, if the relevant or the PG info T belongs to another OSD, we'll query that OSD for that log, for its log. Otherwise, we will, if it's our log, then we'll use our log as the authoritative log. So once we have that log, we will get a, just bear with me a second. We'll get a got log event. So if we look for that, so that gets posted after choose acting and therefore subsequently find best info have run. So they run up here. We can then post an event got log if we know that we being this OSD that we're running on, this instance of the PG on this instance or this OSD knows that its own log is the authoritative one, therefore it posts the event got log. The other place where that event will be posted is once we've received the log from the other PG on another OSD that we've determined to be the authoritative PG. We'll request a log from that. Once we get it, we post a got log event. Then we react to that event down here. This is our reaction to the got log event. We leave get log and we transition or we call process master log. So in process master log, we merge the authoritative log with our own if that's necessary. Yeah. Yep, so we merge that log and we then transition to get missing, the next state. So you can see that once again here. We're in get log, so we were in get info. We got a got info event. We transitioned to get log. We then successfully executed find best info. We worked out the authoritative log. We requested that log if necessary, from a remote or one of the other OSDs that in the I've drawn a blank. We've requested from the OSD that we've decided has a copy of the PG with the authoritative log. Once we receive that back, we get generate a got log event and we transition to get missing. So we look at get missing. We then iterate through our acting recovery backfill targets. And then we worked out our missing set and also what we need to do to achieve backfill. So in this condition, we've determined that we don't need, well, that we need to completely backfill because we have an empty missing set. We look for divergent updates. We request the missing set and the full log from each of the OSDs that we're peering with. In this case, we've determined we need it up through. So up through is a field within the PG info T that we need to request. We need to request the monitor to update our up through in our PG info T. And in order to do that, we post the need up through event. And when we do that, we transition to this wait up through state. We've accomplished all of that. We can post the event activate, and that includes the epoch. So if we look at the definition of activate, this is actually, activate as an event. So we're creating an activate event, and we can see that this activate event, which is here, takes us into the active state. So we can see that by looking at right. Yeah. So this event is actually being captured by the peering state. So we're well down into get missing, we post this event and peering reacts to the event. So when peering reacts to the activate event, so we're posting the event, activate. Okay, here we are. No, that's replicas active. Actually, maybe it's... Oh, sorry. We haven't defined a reaction for that transition. It's just a simple transition. So when we receive this line defines that when we receive the activate event, we transition to the active state. This is why you've got to look at the header declaration for a state, as well as the definition in the source file, because these transitions can be defined as a reaction to an event or just a simple transition where we just say, okay, if we receive an activate event, we transition to active. So if we look at the active state here, it has a default transition to activating. So we now need to look at the activating state. Okay. So it has no default transition, so we want to look at the definition. Activating. So activating, okay. Wasn't in, sorry, I'm a bit confused. Okay, so this is a constructor for active. Okay, so this is where we're actually activating in the constructor of the active state, even though we transition directly to activate. We do some work in the constructor of the active state. We do a few checks, and significantly call activate. And if we look at the definition of that function, which is 9, we can see we once again do some checks, some asserts. We clear the down state. If we're the primary, we update our last epoch started. So at this point, when we update that last epoch started, we are acknowledging that we have an authoritative history of this PG. And so if we go through the peering process again, at some point in the future, we will be considered the best or the most authoritative OSD to query for an authoritative log, because at this point in time, we have decided that we are ready to go active and that we have an authoritative history of this PG. sorry if I keep repeating the same thing, but it's important to get that concept, and it's kind of difficult to wrap your head around, especially to begin with. So once we've done that, update a few of the internal values, including our last rollback. Then we create a, I forget what we call that. What do we call that, Josh? That the C that this stands for a completion? Yeah, completion. So we create a completion that is going to trigger when everyone has committed. Then we do some housekeeping to do with snaps and recovery. But the main thing is we've completed that we've created that completion. Go on, do a lot of housekeeping, log weirdness, which is basically if we find any values that are a little bit strange, we log them. Or we create an error, but it's just an error. We don't change anything we're doing. It doesn't have any effect on what we're doing. So we just log the fact that we've found some strangeness. So how often we see that when it's not in a testing environment, I suspect we don't see that very often at all. So we then start where we start up the replicas, activate the peers. So we'll send them a message to activate. Okay, that else if statement we're going to ignore. It missing. So this is recovery rather than peering. So then we're finished with that. So if we go back, completion. Okay. So PG activate committed. So if we look for all instances of that symbol, we can see that in its definition, when that completion triggers, we call activate committed. So if we look at the definition of that, so if we've reset since, we basically don't do anything. But if we haven't and we are the primary, we insert ourselves as an activated peer, and we make a note that activation is committed. And if this is the last, if we are the last peer to activate, we call all activated and committed. So if we look at that point, we know that all peers have activated and they have committed the info.last_epoch_started. Now we can update info.history.last_epoch_started, which, as I mentioned before, is an indication that the PG as a whole, so in other words, all the OSDs involved in the PG or involved in the custodianship, if you like, of the PG, for want of a better term, all of them have activated, all of them have committed last epoch started. So that's what's required before we commit history.last_epoch_started. So we do some checks. Make sure we are not degraded. And then we queue an event, which is all replicas activated. So if we look at that event, it gets caught or the active state reacts to all replicas activated event, and it then sets its info.history.last_epoch_started to last epoch started. So they should always match, but depending on OSD's flapping and the timing of things, they may not match. So if we have an info last epoch started that is greater than the history.last_epoch_started, we know that that PG on that OSD went active, but it was not active long enough to receive an acknowledgement from the other PGs in the acting set that they also went active and wrote down the last epoch started. So we have to be able to handle that case when we're peering and determining which is going to be the authoritative log. And once we get there, we're active. And that basically is the end of peering. We then determine what recovery we need. We determine what backfill we need, or we determine that all replicas are clean and that we do not require any recovery. And in that case, we issue all replicas recovered. That gets interpreted. error. Okay, so recovering reacts to that. More replicas recover to then there, yeah, that then transitions to the recovered state. Transitions to recovered. So we've transitioned here to recovered, and then the next step is to transition to clean. So once we do that, we're active and clean. We're peered, we're active and clean, we're up and running. Well, we were up and running as soon as we all went active, but that's basically the end of what I was going to talk about today. So we've gone a little bit over time, but not too far. So anyone have any questions? Or have I put you all to sleep?
Tim here. I don't have any questions, but I wanted to say thanks for going through that. I've not looked at the guts of the OSD code in detail, so it's in some respects it's a little bit baffling for me. But at least I think now I've got a good idea of I've got somewhat of a feel for how this thing hangs together. So if I do have to go looking in this code, at least I think I know where to start now, which I didn't before. So that's helpful.
Yeah, look, don't feel bad about feeling baffled. I think anyone who approaches this code for the first time is baffled. I think that's a very good description of the initial state of someone who initially starts looking at the state machine. Yeah, it takes a little bit of getting used to, but once once you get used to it, it's quite a, you know, it's a good solution to the problem. And it's quite straightforward once you understand how the transitioning between states works. And this graph is key to that. The visual representation. Without that, it would be enormous. Well, it would be difficult, more difficult. You know, this helps to shed some light on it. So handy to have this around if you're looking at this code, that's for sure.
Yep.
Thanks, Tim. All right, well, I guess...
Hey, Brad, so where can I get hold of this picture?
It's here. So docs.ceph.com/docs/master/dev/peering, and it's at the bottom there. You can see it. It's not particularly readable, but if you download that image, you can scale it up.
Okay, thank you.
No problem. All right, my BlueJeans seems to be a little bit frozen. So I can't do anything with BlueJeans at the moment. So if no one else has got any other questions, if we can at least kill the recording or maybe stop the entire thing. I can't. All my buttons on BlueJeans are not.
Yeah, I can take care of that. Thanks, Brad. Thanks for going over this code, and I'm sure it's useful to a lot of us.
Thanks, Neha. I can't see the participants, so I'm not exactly sure who's on the call, but if you have any ongoing questions, let me know. Always happy to talk about this sort of thing. And I hope the explanation was reasonably lucid and reasonably easy to follow.
Yes, I think it was. And we don't have any outstanding questions on the chat for now, but if anybody has any more questions, feel free to reach out to Brad over email IRC.
Definitely. All right, well, we'll call it a day.
Sure. Thanks again. Thanks for joining, and thanks, Brad.
Very welcome. Thanks, everyone.
Thanks, Brad.
Thanks.
Thank you. Thanks, Brad.
Thanks, Brad.
Bye-bye.
Bye.